When you interact with a large language model, the experience is defined by the fluid, human-readable text streaming across your screen. But beneath that interface, the system is blind to the words themselves. It operates entirely on massive arrays of floating point numbers. Within this numerical environment, the system is effectively a calculator processing statistical patterns. It does not recognize the definition of a word, only the mathematical relationship between the digits representing it. To understand how these machines generate coherent language, we need to trace the mechanical pipeline that converts raw text into purely mathematical calculations. This sequence begins with raw text, fractures it into tokens, converts those tokens into vectors, and processes them through transformer nodes to predict an output. For engineers tasked with deploying or scaling AI infrastructure, grasping this math-to-text pipeline is a requirement. The physical hardware decisions depend entirely on these underlying calculations. The first step of the pipeline begins when the model ingests a raw, continuous string of human language. Because a processor cannot calculate an entire sentence at once, the system performs tokenization, the process of fracturing sentences into discrete functional chunks. A token is not necessarily a whole word. It might be a syllable or a single character. It is simply the smallest unit the architecture is designed to ingest. This step is the bridge that prepares unstructured human language for a strict mathematical translation. After tokenization, the system uses algorithms like word-to-vec to assign each token a specific sequence of numbers. These numbers act as coordinates, plotting tokens into a high-dimensional vector space called an embedding space. Geometric proximity means semantic similarity. Points for dog and cat are physically closer than airplane. Over time, related concepts pull into tight clusters, pushing irrelevant tokens away. Mapping language to these coordinates allows the system to perform semantic search through pure distance calculations. These geometric embeddings are the mechanism that enables a math-only engine to associate related terms without requiring a human dictionary. In a newly built model, the starting vector coordinates for tokens are often incorrect, leaving the map in a state of chaos. For example, an untrained model may mathematically fail to distinguish between the coordinates of a dog and a cat, treating them as unrelated data points. Through iterative training on massive volumes of data, the model forces these coordinates to shift into their optimized clustered positions. This spatial shift is driven by massive-scale matrix multiplications, a relentless series of calculations that update the value of every point in the system. Standard processors are not designed for this density of simultaneous calculations, creating a physical bottleneck for the software. Because of this density, GPUs are mandatory. Their architecture is specifically designed to execute these large-scale mathematical workloads in parallel. The model's capacity to learn and improve is tied to the volume of matrix multiplications its hardware can sustain. However, static embeddings have a limit. They cannot distinguish between identical words used in different contexts, like bank referring to a river or a financial institution. The transformer architecture was developed to solve this specific limitation. The transformer uses a mechanism called attention. Attention weighs the relationships between all words in a sentence simultaneously. If the surrounding tokens include money or interest, the system mathematically reinforces the financial meaning of bank while dimming the connection to river. This differs from older architectures that read text sequentially, making them slower and less effective at maintaining long-distance context. Attention dynamically adjusts the math behind a word on the fly, determining its meaning based on the token surrounding it. This architectural leap is what allowed numerical models to finally navigate complex linguistic context. When we zoom out, we can see the endgame of this entire pipeline: next token prediction. The system uses the context weights from a transformer to calculate a probability distribution, identifying the most likely token to follow the current sequence. This is an autoregressive loop. The newly predicted token is appended to the sentence and fed back into the start of the model to trigger the next calculation. This cycle repeats, generating one token at a time until the sentence is complete or the token limit is reached. Moving this from a theoretical model to a production environment requires significant physical resources to maintain that continuous loop. Since generating every single word requires millions of real-time matrix multiplications, developers must rely on dedicated hosting infrastructure. There are three primary deployment models: self-hosted, cloud-hosted, or model provider-hosted, each offering different levels of control over GPU compute and data throughput. Choosing between these options requires engineers to calibrate their model selection based on their specific use case and hardware access. Deploying these models effectively means bridging the math of token prediction with the physical realities of GPU infrastructure.